Have you ever stopped to think about the invisible forces that are constantly shaping our world? I'm talking about everything from the weather patterns in the sky to the very blood flowing through our veins. Well, that's what we're diving into today, the incredible science of flow.
I mean, really think about that for a second. It just doesn't seem to make any sense, does it? You have this gigantic, heavy object made of steel just sitting on the water's surface, while a tiny little rock drops straight to the bottom. How is that possible?
And then there's this. How on earth does a machine that weighs hundreds of tons, literally more than a herd of elephants, just lift off the ground and soar through the air? It feels like magic, but I promise you, it's pure physics.
Well, the answer to both of these incredible puzzles and a whole lot more is all wrapped up in a field of science called fluid mechanics. It's the study of how fluids behave, and trust me, it is absolutely fascinating.
Okay, so let's really break this down. Before we can understand how things float and fly, we need to get on the same page about what a fluid even is.
You know, the first thing we got to get straight is that when scientists talk about a fluid, they aren't just talking about water or oil. The word actually includes any substance that can flow. And that means gases, like the very air we're breathing right now, are fluids too. That's a huge concept to lock in. And the big difference between them really just boils down to how their molecules are arranged. In a liquid, the molecules are all packed in there pretty tight, which gives them a set volume. But in a gas, the molecules are super spread out, zipping all over the place, which is why they'll expand to fill any container you put them in.
Okay, so you put all that together, and that's what fluid mechanics is all about. It's the science that covers how all these liquids and gases behave. And we usually split it into two big areas: fluid statics, for when fluids are just sitting still, and fluid dynamics, for when they're on the move. All right, let's start with fluids that are just sitting still. Fluid statics. This is going to help us solve that first big mystery. How in the world does a giant steel ship float?
You want to know the secret? It goes way back, over 2,000 years, to a guy named Archimedes. And his principle is brilliant. It basically says that when you stick an object in a fluid, like water, the water pushes back up on it. And the strength of that upward push is exactly equal to the weight of the water the object moved out of the way.
So you can literally picture it as a tug of war. You've got gravity pulling the object down, that's its weight, and you've got the fluid pushing up with what we call a buoyant force. If the weight is stronger, the object sinks. Simple as that. But if that buoyant force is stronger, or even just equal, it floats. It's the exact reason you feel lighter when you jump in a swimming pool.
And this is the light bulb moment, right? A tiny pebble is solid and dense, so it only pushes a tiny bit of water out of the way. The buoyant force is super weak, and it sinks. But a ship is mostly hollow inside. That incredible shape allows it to displace a massive amount of water, creating a buoyant force so powerful it can easily hold up all that steel. It's all about the shape.
Okay, so that's what happens when fluids are just hanging out. But things get really interesting when they start to move. And it turns out there are two totally different ways that fluids can flow.
Think of it like this. On one hand, you've got laminar flow. It's smooth, it's orderly, it's predictable. The fluid moves in these nice, neat, parallel layers. Just picture thick honey slowly pouring out of a jar. And then you've got its wild cousin, turbulent flow. This is chaotic, messy, and full of swirls and eddies, like water blasting out of a faucet at full tilt.
Now you might be thinking, okay, smooth versus chaotic, I get it. But for an engineer designing a pipeline or a race car, knowing which type of flow you're dealing with is a huge deal. It changes everything. So the big question is, how can they possibly predict which one is going to happen?
Well, they use this absolutely brilliant tool called the Reynolds number. It's what's known as a dimensionless number. Basically, it's a pure ratio that lets us compare the forces that are trying to get the fluid moving versus the forces that are trying to slow it down. And what's so cool about this is that by calculating this one number, engineers can know with amazing accuracy what the flow is going to look like. If you get a low Reynolds number, say under 2300, you can bet on smooth, laminar flow. But if that number gets high, over 4000, then you better get ready for a chaotic, turbulent ride.
Okay, so with all that in our back pocket, we can finally tackle that second big mystery from the beginning. How does a massive 500-ton airplane actually get off the ground and fly? And the absolute key to understanding flight is another giant of fluid dynamics, Bernoulli's principle. Seriously, this one is a game changer. It basically tells us something that feels a little counterintuitive. As a fluid starts moving faster, its pressure actually goes down. Faster fluid, lower pressure. Remember that. So here is how an airplane wing, or an airfoil, pulls off this magic trick. Look at its shape. It's curved on the top. That means the air that goes over the top has to travel a longer distance. So it has to move faster than the air underneath. And what did we just learn from Bernoulli? Faster air means lower pressure. So now you have low pressure on top of the wing and higher pressure below it. And that higher pressure pushes the wings straight up. That push, that's lift.
So, floating ships, flying planes. Pretty cool, right? But believe me, these principles aren't just for big machines. They are everywhere, in technologies we rely on every single day without even thinking about it.
I mean, just look around you. We're talking about the aerodynamics that make our cars more fuel efficient, the design of wind turbine blades and hydroelectric dams that generate our power. It's even fundamental to medicine, helping us understand blood flow, and to meteorology for predicting the weather. It is the invisible engineering that makes modern life possible.
And don't think for a second that this is all old news, stuff figured out centuries ago. Not at all. As this quote points out, it's a field that's constantly pushing forward, with new challenges and incredible discoveries happening all the time.
In fact, in modern engineering and manufacturing, one of the most powerful tools we have is something called computational fluid dynamics, or CFD. It allows engineers to run incredibly complex simulations on supercomputers, visualizing how fluids will behave around a new jet or a race car, all before a single physical part is ever made. It's a total game changer.
So as we push the boundaries, designing faster planes, more efficient energy systems, and even tiny medical devices that work inside our own bodies, our ability to master the flow of fluids is more important than ever. The principles might be timeless, but the real question is, what amazing things will we build with them next?